Okay, so in this problem, we're going to be combining some of the knowledge we have acquired in Hooke's law, so springs, and we're also going to have this kind of structure in 2 dimensions. So the idea is to find out what all the reaction forces are going to be as a result of this external force acting on our beam. So we have a fixed support on the left, we have 2 springs of the same stiffness on this right hand side, and then both of them have the same unstretched length. So we need to first of all, we need to start off by drawing the free body diagram, because we need to know exactly how many forces are acting on this body. So we're going to have the external force here, which is acting at some angle theta, and it is located at some distance L from point A here. And then we have some other distance here, and this distance is L on 2. L on 2. Okay, so first of all, what are the forces that result here on this fixed support? Well, we're going to have a vertical reaction force, and it should go up because the vertical component of this one is going down. So let's call it RAY. And we're also going to have a horizontal component, because for a fixed support, we always have a horizontal component or horizontal force reaction. So let's call it RAX. RAX. Now the next thing we want to do is we want to try to find out what are the forces that are going to be exerted on this end by those 2 springs. So let's think about how this beam is actually going to move for a second. So this force is going to cause some kind of rotation in this manner, so in this direction, which means that this end of the beam is going to go down, and then basically this spring is going to get stretched downwards, whereas this spring is going to be compressed downwards. So compression force, the restoring force of the spring, is going to be going upwards, because it is going to try to counteract that motion so as to return the spring to its unstretched length. And then this one is going to be the same. This one is going to be stretched beyond its unstretched length. So it follows that its restoring force is going to be pulling up. So we're going to have, let's call this one force 1, and let's call this one force 2, because we know that because this one is getting stretched, this one is getting compressed, we don't know whether the 2 forces are going to be the same. So this is essentially what our free body diagram is going to look like. Now what we can do is we can start using some equilibrium equations to find out relationship between the forces in terms of this external force. So let's do sum of the forces in the y direction first. So y direction upwards. Okay, so we have RAY, then we have minus F sine of theta, and then we have the 2 forces F1 and F2. Okay, so far so good. So we can say that RAY is going to be equal to F sine theta minus F1 minus F2. So now we need to find out what those F1 and F2 are. Now let's do the sum of the forces in the x direction. So we're going to have this force is going to the left, so RAX goes like that, and then we have the horizontal component of the external force, so that's going to be F cosine of theta, and that implies that RAX is going to be equal to F cosine of theta. So we already solved for one of the forces in terms of the external forces. That's good. And now what can we do? Well, we know that we can take some of the moments about some point, so let's take them about point A. So let's take some of the moments about point A, and let's choose a direction. Well, I'm going to assume that positive is going this way. Doesn't matter which way, it's gonna turn out to be the same in the end. And we're gonna take, well, we have the distances here, so we have the vertical component of this force going down at a distance L, so basically this is gonna cause a rotation in the other direction, so we're gonna have minus L F sine of theta. That's one of the forces, and the other force is going to be these 2. So we have L plus L over 2, so that's 3L over 2, and these ones are actually going to go in this direction, so we're gonna have 3L on 2 of F1 plus F2. And now you notice that we can cancel out this L, because if we divide everything by L, the L disappears, and we can solve for F1 and F2 in terms of this external force, F sine theta. Okay, so that seems pretty straightforward. Okay, so that all seems good. So what we could do is we could actually plug this expression back in here, or even in here if we make it in this way. So we have F sine theta minus that. So we know what that expression is. So this implies that RAY is going to be equal to F sine theta minus 2 over 3 F sine theta. So this is 1/3 of F sine theta. So we already solved for RAY. But look at what we have here. We have two forces. We don't know what they are. We only have 3 equations so far, and we haven't found out what either of them is. So what are we going to do? We don't have any more equilibrium equations here. We could take some of the moments about some other point, but that wouldn't really help us, would it? So what else could we do? I mean, we really have to think about what's gonna be happening here. So one of the things we can do is derive a compatibility equation. So what you can imagine is that on this end, so let me draw this here. We have our original position of the beam. Once we apply the external force, this beam is going to rotate a little bit. You can imagine this is going to bend by a very, very small amount. Let's say some angle alpha. And that's a very small angle. And what's going to happen is you're going to have a spring here that is going to get stretched. So it's going to look something like that. And then you're going to get a spring here that is going to be compressed. So it's going to look something like this. But the interesting thing is that you'll notice that this displacement here, let's call it delta, is going to be the same for both of those springs because they're both connected at the same point and they both have the same stiffness K. So what's going to happen here is delta is going to actually be the same displacement for both because of the common point of connection between the two. So this spring is going to get stretched by an amount delta. This spring is going to get compressed by an amount delta. So we can say, well, F1, which is the force on this stretched spring, is just going to be K times delta. And this is going to be going upwards because we know the force is just going to go upwards. This one is going to go upwards as well. And now F2 is also going to be equal to K times that displacement delta. So it turns out that simply by deriving this very basic compatibility equation, we've managed to find out what those F1 and F2 are going to be, and it turns out that they're going to be equal to each other. So this is the fourth equation that we needed to derive in this case. And we can say, well, if both of them are equal, then that implies that F1 and F2 are both going to be equal to 1/3 of F sine theta. Because if we plug this here, this becomes 1 plus 1, that's 2F1, then divide by 2, and it gives us the value of one of them. So that's it. That's how you solve this kind of problem. So sometimes it might not seem so obvious what you need to do. So if you notice that you run out of equilibrium equations like this, what you can do is you can try and derive all the things related to how things are displaced or how things are deforming. But we won't be doing this in statics a whole lot, but in solid mechanics, we'll be doing it quite a lot because sometimes we won't have enough equations, and if we want to solve for everything, we need to derive new equations that are going to give us the values that we need.